So volume of solids. Okay. Okay, this volume of solids, we stick first with this one here. Solids of revolutions. Okay. All right. So what is solids of revolutions? For example, this one is easy. There's a code. Okay. So this code is obtained by, imagine that you have a line, it's half a line, and then you revolve this around x-axis. Okay. Say y equals x over 2, for example. You revolve around x-axis, so then you get a between, say, x, say from 0 to 4 as well. Rotate and you get a cone shape like this. Okay. And sorry, I should say you're not rotating the curve, but rotating a regions. So you get a, now, and you rotate regions, now you get a solids. Solid of revolutions. Right. So this is how what we meant by solid of revolutions. Okay. So our objective now is how to compute solids, the volume of solid revolutions. Okay. Solid revolutions, fixed axis. This is the axis. Okay. So uh, when you revolve a, say, a half circle, including the, not the half circle, but the disk, half disk, then you get a ball. Okay. That's what I meant by solid revolutions. Okay, so let's call this one here. Let's redo the example. So we're going to this y equals x squared square root of x. Okay, between the line x equals 4 and x-axis. That's wrong. Right, so I should say this is split. Okay, so first we need to sketch the object. So how we get this one? Okay, so y equals square root of x. So this the curve looks like this one. Okay, so between and x line x equals 4. So this is the region. Okay. Okay, and then revolve around x-axis. About x-axis. Okay. So at the end, you get an object that looks like this one. Okay. It's a solid here. Okay, so you have a volume that you need. This is what the thing that we need to compute. Okay, so how we proceed is one. So we use the fourth step of the partitions and then take samples, compute for one sample, sum it to get a Riemann sum, and then take limit to get the integral. All right, so we see that. Okay, so first thing is partitions. Partitions is so because we know this is clear from the examples, we partitions x uh, between 0 and 4. And we take a sample. Seconds. Sample is this one. Okay. So what if our sample is rotated, revolving? So here it becomes a disk. That's our sample. Okay. So our sample looks like this one. Okay. And what's the radius is or equals what? Say that's the height of this. Is the so the radius is the y. Is equals y equals square root of x. Okay, and the width of this is delta x. Okay, so the volume for this, we call it dV. Okay. So that is the pi r squared. Okay. So that means this is pi square of this, just x. So that's the delta v, just one volumes. Okay, so sum it up. Riemann sum. So the whole value would be approximated by Riemann sum. So according to the partition, the summation is done. So pi xi delta I. So that's the estimate for the sum. And then take limit. As you take limit, then you get the volumes. limit. Let's do this. Get integral. You see this x always between 0 and 4. 0, 4. Okay. So phi x. Get, let's see this. Let's compute this quickly because these are x squared, so 1/2 x squared. So pi over 2 x squared. And you plugged in this bound. Okay, you plug in 0, there's always 0. This is 4. So you get, okay, so that's the volumes. Okay, so this technique is called the, let's go back to this. Method of disk. Because you cut the object into this of the into thin disk and then compute each thin disk and then sum it up. All right. All right, so let's do this example. Okay. Slightly smaller. Right. All right, let's do it quicker now. Okay, you have a parabola. So you have a let's do parabola here. This picture. Is y x squared. That's the usual parabola. And uh, y squared equal 8x. Okay, so this. Okay. So this region here. Okay. And revolve about x-axis. X-axis. So that's important informations. Revolve x-axis or y-axis. All right. So we'll see. Um, let's do this one here. So partitions. And we need to compute this point here. So compute the intersection because this is 0, you know. This one is, let's see how we compute that. Y equal x squared and y equals 8x. So y squared is 8x. So we need to, so y squared is y to the fourth. Find those sections. Y. Mm, 8x. Okay, so equals 0. So let's take this out. 8 equals 0. Okay, so x equals 0 and 2 is 2. Okay, and let's see. Um, and then just take one sample. Okay, so one sample is, say, this one here. If you revolve this the sample around uh, about x-axis, well, should put this a little bit. Yes. If you revolve this, what you get is object looks like this one. Okay, so our sample here is now a, it's not really a disk because you have a whole disk. Okay, so this is a delta. And let's see, this is the big disk. So the big radius. The big radius is the green one here. So y equals square root. Let's see. And the small disk is this one here. X squared. Okay. So the volume for this is large disk. Delta X. That's our delta volume. Okay. So in this case, the pi, taking pi out. So r square is square of this would be just 8x. And here r square just x to the 4 delta x. So that's our sample, volume sample. And 3 Step 3 is Riemann sum. So our volume is approximated by the Riemann sum. Oh, sorry, this is for x between 0 and 4. Summation according to the partition P, xi minus x 4 delta ix. So that's the Riemann sum. And then the last thing is the volume. Okay, so V equals integral, because x is between 0 and 4, you can take the constant out. There. Okay. Is that okay? So this is what we call method of what we call this is for washer method. Why called washer? Washer is this. So it's called thin disk or thin washers method. Okay. All right. Same problem here, but instead of x-axis, revolve it around y-axis. So revolve around the same thing here, but revolve around y-axis. Okay, so y-axis. So in this case, the picture would be square root of 8x. Okay, this we know this is 2. This is 4. Revolve around y-axis. Okay. Let's do this. You can hit this one, and you get the same thing, right? Similar, not the same, but you get the similar way to compute this the volume of revolutions. But what we do here is slightly different. So let's partition this one. So this is the example. But if you revolve around y-axis, this is what you get. Of course, this is not a disk or washer. Okay, or washer. But we try to compute this one here. Okay, so partitions. Second is sample. Okay, our sample is now looks like this one. Very thin. Okay, so how we compute the volumes? All right. Let's see. Uh, what we do here is that we cut this up. So you use scissor to cut this. Okay. If you cut this up, you get a rectangle. Okay. It has a slightly width, so thin. Okay. So it's nice of paper. All right, so let's compute this one. The length would be the circumference. Let's R be R would be distance from here to here. So that's x xi. Positions xi, and then the height would be, all right, so the top minus bottom. The top is y equals lower. That is, top is square root of 8x. Minus the lower one, the red one, is x squared. So that's our, and the thickness is delta. Okay, so this is 2 pi r, meaning that 2 pi times x. Okay, so the thickness, sorry, not thickness, the height is this one, and the width is delta. So the volume of the sample is, let's see, 2 pi xi times this height times the width. Okay. And there's the width. And the third one, Riemann sum. So V is approximated by this Riemann sum. This Riemann sum partitions, so 2 pi this is x between 0 and 4, right? Sorry, 0 and 2, not 4. Oh, did we correct? All right, this is incorrect. This is the one that full bus. Okay, so this is the Riemann sum, and then take limit. You get the volumes. V equals. So take the 2 pi out. Integration from 0 to 2. X times x minus x squared dx. Okay. Any questions? See that you don't need to memorize any formula except formula of somehow uh, this related, so something that the u revolves. So area of square, sorry, area of square, of course, area of disk. Okay. Others. Questions? All right, so that's the what we call the method of Lucas's. I forgot what's the name for this. Method of oh, okay, so this is shell. So this is shell method. All right, and the last one is cross sections. Let's just do one example from the book. Okay, so let's do this one. Okay. Okay, you have a solid. The base is on the first quadrant. Okay, so on a regions bounded by this 1 minus x squared over 4, x-axis and y-axis. So let's draw this. So this is this one. If y equals 0, then it is x equals 0. So this is 1. X equals y equals 0, then this is just 2. It's uh, bounded by this region. Okay. All right. Suppose the cross section perpendicular to the x-axis. So that means you have nothing this way. cross sections is a square. Okay, so the object should looks like, if you cut this out, oh, sorry, this is a square. Okay, find the volume of the solids. All right, so that means we partition the y-axis up here. That's the sample, and the object would be a square like this. Okay, so partitions. The y-axis between 0 and 1. Okay. Second is sample. All right, so the sample would be, okay, this is y actually. Sorry. Okay, this is the side of the, okay, this one. Okay, that is the x. X is, let's see. All right, so let's y equals 1 minus, but now we need in terms of x. Okay, so x x4 4 times the y. All right. Okay. Right. So x is 2. Okay. That equals to. Okay. So the area of this, of course, is the, let's give you 4 columns, and the square would disappear. Oh, sorry. Okay, because the width here is, okay. All right, so that's one sample. Riemann sum. Will approximate the volumes. That is related to P. Sum is 4 minus y. That's mass is limit S P zero. You will get me the volumes. That is the integral. Okay. Now because we partition from 0 to 1. Take 4 out. Okay. So then you can compute this. Okay, this is method of slabs. Well, parallel tab or something. All right, so you don't have to worry about the names, okay? But uh, always uh, go back to the steps. Partitions, take sample, compute for one sample, sum it up, and take limit. Always. Okay, questions? Okay, if not, then we'll stop here. I will add some more material, put that on the video or just notes uh, containing some problems and an answer. All right. Okay. Stop the recording.